All right. So I'm Thierry. I'm from Belgium, country that is on the non-enviable first place of having the longest time without a federal government, 500 days. We make sure nobody can beat us, and after every election, they're trying to beat the record, like. Right, but more interestingly, it's also the country of chocolates. So you have chocolates on the table. So if I mess this up, at least you will remember me, oh, it was good chocolate. So it's dark chocolate, it goes well with the coffee, with black coffee. Interestingly, it also goes very well with smoky whiskey. So that's it. So I'm starting by being vulnerable. It's a little thing I do because I'm very stressed at public speaking and I need to do this. So I'm bloody shy and I'm an introvert. So this is quite challenging for me. Well, in fact, I dislike public speaking quite a lot. And each time I am in front of it, I feel totally miserable. And I'm like, why am I doing this? And I keep doing it because, well, what can I say? I love having spoken. It's just like, okay, that's it. Now I can start. A couple of years ago, I started this presentation. Somewhere end of 2016, feature branching is evil. I got the idea for the title when reading an article from Jess Humble that is called on DVCS's continuous integration and feature branching, where he starts his article by saying, well, I would like to say to people, feature branching is evil, just to get their attention. But in reality, I lack the determination and the confidence to be a zealot. And when I read this, I was like, let's fix this. Now, this was a bit pretentious from me and a bit naive because, well, the first time I presented this, I absolutely didn't felt confident and I felt like really, really small. Well, who was I back then? Nobody knew me. Well, still, nobody knows me, but whatever. But yeah, by now, it's a presentation I've given the most. I've lost track how many times I've given it. It's also the presentation that gets the most rejected in call for presentations. It's a very hard sell, especially in developer conferences. Don't know, probably too confronting, I don't know. I never get feedback, so I don't know. But it unlocked quite a lot of conversations and quite a lot of discussions. And people kept asking me, well, actually, how do we get to trunk-based development? Which is essentially saying, how do we realize continuous integration as it should be? And so I kept repeating the same things, kept repeating the same techniques, the same practices, and I was a bit baffled by how little engineers know about the practices that are required to commit safely into mainline without creating chaos. And I was also surprised to realize that, well, actually, this information is scattered over many, many books and many, many articles, and there is nowhere a single source that centralizes this knowledge. And so this led me to write down what I thought are the practices that are required to reach continuous integration. And I wrote this down late 2020 in a draft article, and I showed this to my very good friend, Steve Smith, and he was like, wow, I like this. It's very detailed, really good. However, you're running the risk of writing a mini book. Well, he says that quite a lot when he reviews my articles, but whatever. Now, it stayed in a draft for another year and a half because I decided to write down feature branching is evil in an article series, which is not finished, obviously. Well, I'm stuck on the next part, which is code reviews, which, well, I have quite some things to say about it. But whatever. At some point, somewhere August last year, I was ready to publish the first article of the series. And here I am now. I've turned this into a presentation, and this is the third time I'm going to give this. So let's start with a little test. Martin Fowler calls this the continuous integration certification test. So who does continuous integration? Raise your hand. Whoops. Keep your hands raised if everyone in the team commits at least once a day into mainline. Whoops. Keep your hands raised if every commit triggers an automated build and execution of all the tests. All right. And keep your hands raised if whenever the build fails, it gets fixed within 10 minutes. Okay, 0. Well, this is actually continuous integration. So this is the test from Jess Humble. So continuous integration is a practice that ensures always working software on mainline, and that gives us feedback within minutes on whether a change broke the application or not. So it allows us to perform on-demand production releases at any given moment in time, and it's actually one of the most important practices to adopt in order to enable the fast flow of work through our value stream and to get closer to a single piece flow. And we know from lean manufacturing that the single piece flow is, well, will predict higher quality and higher delivery throughput. But to achieve this, it requires that everyone in the team integrates their work at least once a day into mainline, leading to multiple integrations per day for the whole team. And each integration should be validated by an automated build and execution of all the automated tests. And whenever the build fails, well, it gets fixed within 10 minutes. Now, to reach this state, the team needs to adopt a certain set of practices. And, well, I arrived to identify 14 practices. And again, my friend Steve suggested, well, look, you'd better split them up in 3 groups. And thus, we have team working, we have coding, and we have building for continuous integration. So, team working. So, continuous integration is actually a team practice. So it's a state we reach as a team, not as an individual. So most of the time, practices are defined for individuals. And when most team members apply the practices, well, the team does well. However, with continuous integration, it's quite different. So it requires that everyone in the team implements a certain set of practices before the team can say they practice continuous integration. And so to achieve continuous integration, well, the team needs to adopt 4 practices. And the first one is version control everything. So obviously, it means we version our production code, but it also means we version our automated tests, we version all the database schema migrations, all the application configuration, all the system configurations, but also all the infrastructure that is required to run our systems, all the documentation and all the run books, and everything else that we need to safely run our system. Now, we would think that by 2023, this is kind of evident. It seems the inverse is still true. Well, usually, it happens that teams mainly working with databases and SQL or working with or having to modify CRM systems, well, usually they have a hard time versioning their code. Well, especially because, well, these tools are not really adapted to version control systems. And they require that you change things inside the system that is then stored inside the database and whatever. So You need to find different ways to version control these things. Now, my last encounter of a team not using a version control system was 2018, so this is already quite a while. But well, Alan Kelly does far more consulting than I do, sees far more organizations than I do, so well, he will have more data on the topic. Now, when we do not version our code, well, we do not have a single source of truth. And so, releasing a piece of software comes down to a marathon of chasing pieces of code on individual engineers' machines or on shared drives. Also, rolling back a deployment that went wrong, well, will be pretty hard because, well, we don't have a single source of truth. And so, well, pretty difficult to go back to the last known good state because we simply don't know what this last known good state is. And lastly, well, all other practices that make continuous integration falls flat because they all depend on version control everything. Now, this is the first practice that actually requires tooling. In this case, it requires a version control system. So actually, there are only two practices that require a version control, that require tooling. So it's version control everything and automate the build. That's all. That's the only thing we need as tooling to implement continuous integration. Oh yeah, by the way, if you have any question, just stop me. We have plenty of time. I've never had so much time to give my presentation. Yeah, well, usually I have to rush my presentations. Now, the other thing I want to note, and I really want to emphasize this, is that, well, a version control system is not only there to version our source code. It's first and foremost a communication tool that allows us to communicate the changes with the rest of the team. And together with continuous integration, well, it will reveal the impact of our local changes on the changes from our other team members. And so, well, it will enable us to gain a shared understanding and to have a collective ownership of our code base, and thus it enables collaboration and communication inside the team, which will inevitably improve the quality and reduce time to market. The second team practice is agree as a team to never break the build. Now, this is absolutely key to reach continuous integration. This is one of the most important practices to adopt. It enables always working software on mainline, and it allows us to perform on-demand production releases at any given moment in time. But it assumes we have a significantly comprehensive set of automated tests so that we gain enough confidence that we are not introducing any regressions when we are starting to commit frequently into mainline. Now, having said this, yeah. Can you pick the mic, because I don't hear you.
So if we've got a sufficiently comprehensive set of tests, would you say there's a maximum sort of time it takes to run them?
Yeah, there is a maximum amount of time. Well, there is a suggestion for maximum time, and we will get to that later on. It's covered, but very good question. Thank you. All right, so having a significant test suite is important, but at this point we are only testing the known knowns, the things we know about the system. But we don't know if the application is actually valuable for our users and how it will behave in front of the users. And that's why it's important to have exploratory testing, which will give us additional information. Now, this practice is non-negotiable. There's no single acceptable reason that would allow us breaking with this practice. Violating this agreement means continuous integration falls flat. And once we don't have continuous integration, our application is broken until someone else proves it actually works, which obviously will add additional time to our lead time, and so will increase time to market, and so we might incur an opportunity cost. Now, to satisfy this agreement, well, we need that everyone in the team runs a local build before committing into mainline, and only commit when the build says success. So obviously it also means we only commit on green. And in order to run a local build and to only commit on green, well, we need to have a vast amount of high quality automated tests. But what is a vast amount of high quality automated tests? If we have many of them, are they of high quality? Well, we'll get to that later on. And lastly, it requires to have a fast build to allow us to commit frequently. Now, when the build is too slow, what happens? Well, either team members do not execute the build, or they execute it less often. But here also, what is a fast build? We'll get to that, and that's also your question. The third team practice is do not push to a broken build. So whenever the build is broken, we stop the line and we fix it immediately. We do not add code on top of a broken build. When we are adding new code on top of a broken build, we are going to trigger new builds, introduce new problems, making it harder to analyze the situation, to find the root cause, and to fix the build. And so we might end up in a situation where the build is broken all the time, or worse, where people are getting used to having a broken build and simply don't care anymore, and so don't look at the broken build anymore. So from this moment on, well, we've lost the monitoring of the health of our application code, and so we've lost the ability to perform on-demand production releases. Inevitably, this will reduce delivery throughput, increase time to market, and, well, we might again incur an opportunity cost. Now, the most crucial practice, or the most crucial step in reaching continuous integration, is to accept as a team that each build, well, each commit should pass the build and should pass the automated test successfully. So whenever the build fails, the team owns the failure, stops all work, stops what they were doing, and fix the build. And only when the build is fixed, they move on. So they take up the tasks that they were working on. So when the build is broken, well, we do not have continuous integration. And if we are adding new code on top of a broken build, well, it keeps the team further away from reaching continuous integration. And as such, well, we are violating the agreement to never break the build. And as such, well, we lose continuous integration. And so our application is broken until someone proves it works. So therefore, it is very important to agree as a team to never break the build. Then the last team practice is, well, revert when broken. So one of the preconditions to continuous integration, so one of the test questions, the last one, is that, well, whenever the build is broken, it gets fixed within 10 minutes. Because, well, the longer the build is broken, the longer it blocks a whole team. And given the salaries of engineers, this is quite a lot of money that is held at standstill. And also it disables on-demand production releases, which is, again, money that we are losing. So it's quite important. Now, not taking this into account as an organization is a sign that the organization either has too much money, which happens, I've seen this, or simply do not care, or what I think is, in most cases, the case is like, well, they are just not aware of how much money they are losing. But why 10 minutes? Why not 5? Why not 15 minutes? Well, this relates to having a fast build. When the build is under 10 minutes, quickly fixing the problem and rerunning the build might work if the fix is easy. However, if the fix is difficult and time-consuming, the quickest and easiest way to fix a broken build is to just revert the last failing commit and going back to the last known good state. But obviously, this requires that we version control everything and that we have a fast build. All right, what are the critical engineering practices to adopt in order to enable continuous integration as a team? So I've identified 6 practices. And the first one is, well, make all changes in small increments. And from my humble experience, helping teams, improving their IT delivery, it seems this is the toughest practice to adopt. It seems to be, well, the most difficult and hardest practice to adopt. But it is also, together with agree as a team, to never break the build, the most crucial practice to adopt to enable continuous integration. So it's essentially breaking large changes in a series of small incremental steps, and this seems hard to do. And the purpose is to keep our application always working while we are performing those incremental changes. So making sure we are never tearing apart the application. So Steve Freeman and Ned Price make this analogy with surgery in their book, Object-Oriented Software Guided by Tests, Growing Object-Oriented Software Guided by Tests, where they say that surgeons prefer keyhole surgery over opening the whole patient's body because it is less invasive and cheaper. But for the same reason, we like to work in small incremental steps because it is less invasive. We are not ripping apart our application, and therefore it is cheaper because we keep our application always working, and thus we can perform on-demand production releases at any given moment in time, which will shorten our time to market. But this is hard work. This will require that we think a bit harder, and we might move a bit slower, but with the immense advantage that we never break the application. We keep it always working, and we can always release. But to make this work, it requires to have a decoupled code base, because, well, it's pretty hard to adopt incremental software engineering skills when the code base is too coupled. And expand contract will help us in breaking large changes in a series of small incremental changes. Now, the central premise of continuous integration is to integrate early and integrate often. So therefore, it's important that we commit frequently into mainline. When we do not commit frequently into mainline, what happens? Well, we start to batch up work and to work in bigger batch sizes. And we know from lean manufacturing that bigger batch sizes drives down quality, drives down delivery throughput. Now, because we work in bigger batch sizes, well, we are going to integrate less often. And so integrating changes become difficult, non-deterministic, and time-consuming. And as such, well, integration times, so the moment where we are going to merge changes, will vary widely. And as a result, well, this will increase time to market. And lastly, well, it prevents communication of changes amongst the team. And so it disables communication and collaboration inside the team. And so we lose collective ownership and a shared understanding of the code base, which will inevitably have a negative impact on code base quality. And once code base quality goes down, it becomes pretty hard to introduce new changes, add new functionality, which will again slow down our team. On the other hand, if we are committing frequently into mainline, well, our change sets are smaller. And as a result, well, merge conflicts will be fairly unlikely, and broken builds will become pretty unlikely. Also, well, because the change sets are so small, well, it also reduces risks. Well, if the build happens to break, finding the root cause will be pretty easy because the change set is so small. But also, it might be we've introduced the failing change just a couple of minutes ago, and so we still have enough context to quickly fix that broken build. And so, well, it will reduce the time that the build is broken. If we do have to revert changes, that too will be easy because the change set is so small. And also, well, because the sunk cost of reverting the change will be pretty low, and this will make it even easier to revert the changes. So all in all, this will all keep the the time that the build is broken pretty short. And so it will avoid that the whole team is blocked for a long period of time. Now, because we are committing frequently, well, it will create a gentle design pressure that will allow us to speed up the build even more, to keep the code base even more decoupled, to work in even smaller incremental steps, and to hide even more unfinished functionality. And so we will end up in this virtuous circle that will allow us to commit even more frequently into mainline. And so, well, it will increase the commit cadence and increase our delivery throughput. A prerequisite to keeping the application always working is to agree as a team to never break the build. And so this requires us that everyone in the team runs a local build and only commits when on green when the build says success. Now, this is where test-driven development supports continuous integration. So with test-driven development, well, we start by writing a little failing test. We add just enough production code so that the test passes to green. Once the test is green, we commit and we push. And then we start refactoring. If the test is red, we revert. If it is green again, we commit and we push again. So test-driven development will create this commit cadence that will satisfy commit frequently, and which is required to reach continuous integration. Now, even when we do not apply test-driven development, it is still vital that we only commit on green. But now, we are moving in the dark. We don't know if our change broke the application or not. And as a result, adding new changes, adding new functionality to the code base will take, well, far more time. And so this will slow down our team. What is more, it will also produce a less effective design. It will be harder to test our code because our code will not be testable, which will again slow down our team. In order to make all changes in small increments, well, it's pretty important to have a decoupled code base. When a code base is too coupled, adopting incremental software engineering skills will be challenging because, well, any change will ripple through all layers of our code base and ripping apart our application for a long period of time. And I've seen this quite often. Like you do one change and then you need to change another thing, another thing, another thing. And at the end, you've touched all the files. Well, the result is that we cannot release at this moment because our application is not working anymore. Now, that's why adopting patterns like ports and adapters, which is also known as hexagonal architecture, is so important. Why it's also so important to apply Canbeck's 4 rules of simple design. And why it's also important to adopt intentional code duplication. All 3 will help us in having a decoupled code base and making sure we have a maintainable code base where it is easy to introduce new changes and add new functionality. Now, from my humble experience, having small methods, small classes, practicing the single responsibility principle and having dependency injection, not using a dependency injection framework, like just dependency injection, will bring us already a long way forward. This will already help us a lot in having good design. Now, we know that adopting those patterns will improve the quality of our code base, but interestingly, it will also optimize engineering time to introduce change because it will be far more easy to introduce new functionality, and as such, it will reduce our time to market and accelerate feedback. If you have to perform a large-scale refactoring that might rip apart our application for a long period of time, let's say we have a method for which we want to change the signature, but it's used randomly at 42 places in the code base, like really a lot. Changing the signature together with all its consumers in one go, well, will take a fair amount of time. Now, during this period of doing this change, well, we cannot release. It blocks us. So one way to solve this, and which most teams are adopting, is, well, branch by version control. So we create a branch, we do the signature change and the change of all the consumers, and once everything is done, we merge the branch back into mainline. Now, there is a risk, however, that in the meantime, someone else introduced a new consumer that was using the old signature. Whoops, what a pity. So a different approach would be to adopt expand contract. Now, from what I've seen, it seems that expand contract is this little unknown gem that few engineers know about, although it's a strong enabler of continuous integration. It's a real game changer. So how does it work? So we start from a situation where we have a method that is used at various places in the code base. So the first thing that we do is we duplicate the method, and we do the signature change on the duplicated method. So we end up with a situation where we have two methods. The old method with the old signature called from various places in the code base, and the new method with the new signature that is nowhere used. This is called the expand phase. We have expanded the code base with an additional method. Now at this point, it's a good habit to deprecate the old method and to verbally communicate with the rest of the team, hey, there is this new method, please use this new method, stop using the old method. Now at this point, the application is still working. We can still release. Then we start to gradually move consumers from using the old method to using the new method. And on each move, we can commit and push. And the application is still working. We can still release. At a certain point, all consumers will have been moved. And so we are in a situation where we have the old method, which is nowhere used in the code base, and we have the new method, which is used everywhere in the code base. So at this point, it is safe to delete the old method. This is called the contract phase. We are contracting the code base by removing the old method. At this point, the application is still working. We can still release. Now, evolutionary database changes like renaming tables, renaming columns, moving columns between tables, splitting columns into 2 columns, 3 columns are all examples of expand contract. Adding a new version of an API alongside of a version 1 of the API with 2 different URLs is an example of expand contract. Blue-green deployments is expand contract for deployments. So we are expanding by adding a new version of our application in production, blue, alongside of the old version, green. We keep blue and green running at the same time until we find blue good enough, and then we contract by removing green. Many breaking infrastructure changes are implemented with zero downtime using expand contract. So, to be honest, expand contract will add quite some complexity to our code base. We will have to think harder. We will move slightly slower, but we have the enormous advantage that we keep our software always working. We can perform on-demand production releases at any given moment in time. And more importantly, we are still able to perform or to add new functionality and release new functionality while we are performing this refactoring. And this refactoring can take days, weeks, or even months to execute. Jess Humble has written an article regarding this. It's called Make Large-Scale Changes Incrementally Using Branch by Abstraction, where he explains how they moved GoCD. So GoCD is a continuous delivery tool from ThoughtWorks. And it used to use as a front-end technology GS template and velocity. and they moved gradually to using Ruby on Rails on the GVM. And how they did that was, well, they just rewrote screen by screen in the new technology. And once a screen was finished, well, they just changed the URL wiring to point to the new screen. Now, he calls it branch by abstraction. Now, my humble opinion about this is that they actually did expand contract. Branch by abstraction is a special case of expand contract. So it uses object orientation with interfaces, but well, it's pretty the same. Now, what happens when feature implementation takes too long? Often it makes no sense to release features incrementally. Now, what happens most of the time is that while teams use branch by version control, so they create a branch, grow the feature on the branch. Once the feature is finished, the branch gets merged back into mainline, and then they can release the feature. Now, the downside of this way of working is that while the feature is being implemented, it is not integrated with all the changes that are happening at the same time. So we do not know, well, we are blind on whether our feature will cause any problems with all the other changes that are happening at the same time. And so we are delaying feedback, and once we are delaying feedback, well, we are going to impact quality. Now, how can we make sure that unfinished functionality does not get released? Because this is actually what teams are trying to do. It's making sure that unfinished functionality doesn't end into production. That's why they are using feature branches. Well, the solution is to just hide unfinished functionality. It's perfectly acceptable to have unfinished functionality sitting in production, even behind a publicly accessible URL, as long as it is not discoverable by the user and that it doesn't introduce any security concerns. But because it has a publicly accessible URL, it can be tested while it is being implemented. So for instance, if we are adding a new screen to a user interface, as long as the screen is not finished, well, we just don't add a menu item to the navigation menu. We only add a menu item at the end when the screen is finished. But because we have a publicly accessible URL, we can actually test the screen before it is integrated in the user interface. Same is true for backend services. As long as the backend service is not finished, well, just don't wire it into a user interface, or just don't call it from another backend service. Only do this when the backend service is finished. Same is true for API endpoints. If we are adding new API endpoints, as long as they are not finished, well, we don't document them. Nobody knows they exist. But sometimes we need to change a widget on an existing screen, or we need to change the behavior of a backend service. Well, this is where feature toggles comes in. So feature toggles gives us great flexibility. It's an enabler of operability and resilience, but with great power comes great responsibility. We have to manage toggles. If we don't manage toggles, it's pretty easy to introduce technical debt and to shoot oneself in the foot, as what happened with Night Capital Services. Anyone heard about Night Capital Services? No? So they managed to lose $460 million in 45 minutes. And they went bankrupt because of badly managed toggles and manual deployments. So what happened was that they reused the toggle between two releases, but with a different meaning, and they forgot to deploy on one of 8 servers. So they had one server running the old version of the software with the old meaning of the toggle, and then 7 others which were running the new version. And so, well, it generated lots of orders that were not supposed to be generated, and, well, bye. How bad technology choices can have organizational performance impact, but like, well, you have no job anymore. Whoops. So, like with work in progress, we like to limit the number of active toggles. So whenever a toggle is not needed anymore, we remove it from the code base immediately. Otherwise, we run the risk of having an application with lots of toggles, no one really knowing wherefore they are used, And so no one daring to remove them. Well, yeah, we might break something. Well, we don't know if we break something, actually. Toggles should be independent from each other. So don't have a situation that to turn a feature on, we have to turn toggle X on, turn toggle Y off, and turn toggle Z on again. So it's very difficult to reason about this, and it creates an insane testing situation. Like, no, one feature, one toggle, nothing more. When we say toggles, well, we say branching logic. Branching logic needs to be tested. So we need to execute our tests against the application with both the toggle on and off. On the other hand, while manual testing should only happen against the next situation that will happen in production. So if the toggle will be on in production, while we do manual testing with the toggle on. Branch-end logic, well, means code complexity, maintainability problems. Well, there are different ways on how to implement toggles. Not all of them are good. Pete Hodgson wrote an interesting article regarding how to implement toggles right. It's called Feature Toggles. It's published on Martin Fowler's Bleaky. Pete Hodgson also wrote a couple of interesting articles about managing toggles, and they are published on the blog of Split.io. So really great articles. What to do, how to manage toggles, the interesting patterns. Right. Okay. In this last part, we are going to investigate the building practices that will support the team working, and especially agree as a team to never break the build, and the coding practices, and in particular, make all changes in small increments and commit frequently. And so the first building practice is automate the build. So first, I want to make things clear. Automate the build is not about having a centralized build server. Having a central build is helpful, but not essential to reach continuous integration. So many times I hear teams pretending they practice continuous integration because they have GitHub Actions or GitLab CI or Jenkins in place. Now, most of the time, they don't practice continuous integration. They just have a centralized build. Now, having said that, it should be possible for any new team member, or well, for any team member in the team to check out code out of version control, execute the build, and run all automated tests with one single command. This is the build script. The build script should produce a single unambiguous result. It is either success or it is failure, not something in the middle, not maybe. It's success or failure. The build script ensures we have a consistent, reliable, repeatable, and deterministic build that we can execute over and over and over again without any side effects. So it is idempotent. It should be treated the same way as our production code. So it is versioned, we apply the same design principles, and it is refactored continuously. It is used, so the build script is used by both the local build on the engineer's machine, as well as by the commit build that is executed on the central build server. So the build script is a prerequisite to run a local build that will prevent broken builds, to satisfy the agreement to never break the build and to have always working software. Automate the build is the second of two practices that actually needs tooling. So in this case, it's the build script. The other practice was version control everything that introduced the version control system. And that's it. That's the only tooling we need. A version control system, an automated build. That's it. It's fairly simple. Now, in order to perform on-demand production releases, well, we need to have always working software. And thus, we need to agree as a team to never break the build. So this requires that everyone in the team runs a local build, and when the build says success, well, we commit on green. So this means that we pull the latest changes, the latest removed changes, integrate them with our local changes, run the build. If the build says success, we commit and we push. So we are effectively integrating the removed changes produced by our other team members with our local changes, and we are trying to detect any conflicts that would happen between, well, any integration conflicts that will happen between the changes produced by our team members and our own changes. Not doing so would defer this conflict detection to the commit build on the central build server. And so we are running the risk that we are introducing a broken build, and so we are running the risk to violate the agreement to never break the build. And once we violate this agreement, well, continuous integration falls flat. And once we don't have continuous integration, our application is broken until someone else proves it works. And so while we are delaying delivery, and we might incur an opportunity cost. Now, whenever we commit and push after successfully running the local build, well, we are going to trigger the commit build that will happen on the central build server. So the commit build is identical to the local build and uses the same build script. So it checks out code out of version control, recompiles our code, re-executes all our automated tests. Now, to avoid context switching, the team member that triggered the commit build, well, should monitor the commit build until the commit build is successful before moving on with new work. Now, therefore, run a local build and monitoring the commit build are a strong argument to have a fast build. The third building practice is have a vast amount of high-quality automated tests. So if we do not have a sufficiently comprehensive set of automated tests, well, we do not know if our changes broke the application or not. The only feedback we get is whether the code still compiles and whether we are able to produce a binary artifact, but that's it. Remember, the purpose of continuous integration is to create feedback on whether a change broke the application or not, and we want to know this within minutes. Now, in this case, well, the only way we know that we have introduced, the only way we know that our changes broke the application is to rely on expensive, time-consuming manual regression testing. And so from this moment on, well, we cannot commit frequently anymore. Did you have a question? No, okay, sorry. So we cannot commit frequently anymore. And so we are starting to batch up work again. And we know from lean manufacturing that if we work with big batch sizes, well, we are going to drive down quality and we are going to drive down delivery throughput. And so, well, increase time to market and introduce opportunity costs. Now, to gain confidence, we are not introducing any regressions when we are committing frequently into mainline, like many times a day. Well, we need to have a vast amount of high-quality automated tests. But what does it mean, have a vast amount of high-quality automated tests? Well, if we have many tests, will they be of high quality? I don't know. Well, it could be that we have many tests, but very little feedback because we are testing the wrong thing. It could be that we have very few tests, but excellent feedback because we are testing the exact right thing. So it is important that we have high-quality tests, that we have many of them, and that they are very fast. Now, to help us with this, well, it helps to apply example mapping. So example mapping will allow us to produce examples that we will use to write our automated tests, and so that we will get high-quality tests, so that we are testing the right thing. And it also helps to have the right roles inside the team, so that we have product managers, test engineers, operations engineers, UX designers, and, well, obviously software engineers. But having all these different roles will give different views on how to test the application and what is important to be tested. And this, again, will lead to higher quality tests. Now, when we are implementing an automated test suite, well, we should consider different kinds of tests. First of all, unit tests. This should be the largest part of our automated test suite. So we should have hundreds or thousands of them. And each unit test should execute in milliseconds. The whole test suite of unit tests, well, should execute in less than 30 seconds. They should not hit the database, neither the network nor the file system. Whenever a test takes a second to execute, it should be a red flag and should require immediate attention. Because, well, once it hits a second, well, you're pretty sure you will end up with an automated test suite that will take you 45 minutes to execute. I've seen this. And it's pretty hard to get it back to 30 seconds. The second set of tests are integration tests. They will test the adapters from ports and adapters. So they will test the integrations with the database, with the file system, or with third-party services. So they will be slower. So we want fewer of them. And lastly, we have the automated acceptance tests. So they are going to test the application in isolation, so without third-party services, but with a database and with a front end. So they are testing the application as if the user is using the application. We have typically hundreds of them, and they execute in less than 10 minutes. Usually, we only implement the happy parts for the acceptance test, because, well, the edge cases should be handled by the unit test. It's just simpler. It's easier to implement edge cases with unit tests. Most of the time, automated acceptance tests are implemented using behavior-driven development techniques. Now, if we want to go the extra mile towards continuous delivery, well, we might consider having smoke tests. So smoke tests are a small set, 1 to 5 tests of end-to-end tests. So they involve third-party services. So we are executing the most important transactions of our application, just to check that everything works right after deployment. So we deploy into production, and then we run the smoke tests as a final check. Okay, and then we can say the release is successful. Now, during the local build and the commit build, so the local build on the engineer's machine and the commit build on the central build server, well, we only execute the unit test, the fast unit test. That's also why it's important that whenever we find a bug, we try to reproduce it with a unit test. Because, well, we want to catch those problems early when we run the local build. Once we have run the local build, we want to have a good confidence that, well, actually all the automated acceptance test will pass. We might consider to have, but that is optional. So we might consider having a small smoke test suite that involves few integration tests and acceptance tests that test the most commonly used features so that we are sure we haven't broken any functionality. But this is really optional, and this is a choice. All right. Now, to commit frequently into mainline, well, we need to execute the local build repeatedly, many, many times per day, in order to satisfy the agreement that we are not breaking the build. And so, well, this requires to have a fast build. Otherwise, you cannot repeatedly execute the build. Now, when the build is slow, two things can happen. Either people do not execute the build, and then we run the risk of introducing regressions, or we run the risk of having a broken build. And once we have a broken build, well, we cannot perform on-demand production releases, which will impact delivery time. Or people tend to execute the local build less often. And, well, then we are reintroducing batch work and bigger change sets. And when we have bigger change sets, we are introducing bigger risks, because if the build happens to break, finding the root cause will be pretty difficult because the change set is so big. And maybe also because we've introduced a failing change a couple of hours, or worse, a couple of days ago. And so we don't have enough context anymore to quickly fix that broken build. And so we end up in a situation where the build might be broken for a long period of time, and we've lost then the monitoring of the health of our code base. Now, because we are batching up work again, well, we are delaying feedback. And once we delay feedback, well, we are going to drive down quality. And once we drive down quality, well, introducing changes in the code base and introducing new functionality becomes pretty hard. And this will, again, slow down our team. But what is fast? Well, 20 years ago, the extreme programming community suggested that the local build and the commit build should take no longer than 10 minutes. Nowadays, Dave Farley advises in optimized continuous delivery that the commit build is under 5 minutes. I would say that 10 minutes should be the limit, 5 minutes should be the focus. If we can get it to 30 seconds, well, we can avoid having hallway SWAT fights, which is quite an optimization of engineering time. Now, we have to take into account that every integration will take 2 builds. One local build on the engineer's machine and one commit build on the central build server. So because of agree as a team to never break the build and to avoid context switching, well, we should monitor the commit build until success. So when the build takes 10 minutes, well, the engineer needs to wait 20 minutes. So this is another argument why we should have a fast build. Now, we may argue that have a fast build contradicts with have a vast amount of high-quality automated tests. Well, the first thing to consider is that, well, our test needs to be fast. That's one. Second, at some point, well, we will have to split test execution in different stages, where in the first stage, the commit build, we only execute the fast-running unit tests. And then we defer the slower-running tests in later stages, like we execute the integration test and the automated acceptance test later on in our pipeline. Also, well, we should consider to remove old, obsolete tests that don't give any value anymore. So many times, teams do not dare to delete existing tests because of the sunk cost fallacy. Oh, look, we have invested quite a lot of time in writing those tests. We are not going to remove them, do we? Well, if they don't have value, why keep them? And lastly, at some point, well, we will have to look at test execution optimization, like parallelization, and look at the performance of our application. Because, well, if tests are slow, it might be that our application is just slow and needs some performance improvement. All right. There is actually a 15th practice that has just been introduced, like last week. So I was lucky that Marit was present in the last time I've presented this at Scan Agile, like a couple of weeks ago. She was present in my session. And she told me like last week, like, oh yeah, we've applied those 14 practices to our team. And there's one thing we have trouble with, and it's flaky tests. And so we came up with a 15th practice, have reliable tests. So like for the build script, well, we want that our automated test suite produces a single unambiguous result. It is either green or it is red, not maybe. Oh, one time it is green. Ah, today it's red. It's red again. Oh, now it's green. No. Green, red. So when tests are not reliable, so which means that, well, we have either to re-execute them in isolation to get them to pass to green, or we have to re-execute the whole test suite a second time, a third time, a fourth time before they get to green, well, this adds quite a lot of time to our total delivery lead time. And so this will increase time to market. And so we might incur an opportunity cost. Additionally, because we are not so sure about the test suite result, well, is it actually green or is it red? It says it is green, but we are not so sure because sometimes it's red. Well, we need to introduce time-consuming manual regression testing. This again adds up to the total lead time. And the worst thing that can happen is that, well, we have a production incident that we cannot solve because we have a flaky test that is red and that we... Am I over time? Because we have a flaky test that is red and that is blocking the delivery, and so we cannot perform production releases. And then the even most worst thing that can happen is that people start to ignore tests. Yeah, it's red, but sometimes it's green, you know. So it removes a safety net. And it also removes, well, the pressure to actually write tests. Yeah, well, why should we write tests? Sometimes it's green, sometimes it's red. Now, how can we solve this? Well, from what I've seen that worked is to split our test suite in two sets of tests. We have a set of stable tests that are very consistent and deterministic. So green is green and red is red. And we have a set of unstable tests that are quarantined. The stable tests are executed all the time, and whenever these fail, well, it blocks a release. However, when the unstable quarantine tests fail, it doesn't block a release. It just gives us information, but that's it. And we only execute them at night. We don't execute them all the time. Now, it's very important that we collect metrics about those unstable tests, like how many unstable tests we have, and that we look at the trend, and it should go down. When it goes up, there is a problem. Just saying. So, as we can see, continuous integration is not a tooling problem, as many teams like to think about continuous integration. It involves many practices that we need to adopt as a team, and we only need two tools: version control system, automated build. All the rest are practices, and this is really the hard part. It's adopting those practices. The tooling part is super easy. You set it up once and you're done. But practices, well, it requires that, well, you practice it a lot so that it starts to become a habit. And this is something we don't do often in our industry. It's practicing. So, each practice is valuable. Each practice is on its own an enabler of continuous integration, but none of the practices stands on their own. They are all intertangled, and they all amplify the benefits of each other. So which means that, well, not implementing one practice will take away the benefits of other practices. But where do we start? Which practice do we implement first? Which one will we implement next? Which one will be easy to implement for our teams or organization? Which one will be pretty hard? Well, it all depends on the unique circumstances and on the unique constraints of our teams. And so to kickstart a continuous integration program, well, we should adopt a continuous improvement framework that takes our context into account, like the improvement kata. So the improvement kata is a continuous improvement framework that helps in implementing organizational change and to measure organizational change. It helps us in reaching goals in uncertain conditions. It was written by Mike Rotter in his book, Toyota Katas. And it consists of 4 stages that are repeated. And it starts by defining a direction, a vision. Something we want to achieve in a far, far future. So in this case, this would be, well, we want to reach continuous integration. So the purpose of the direction is to align everyone on the vision, on where do we want to head, and also, well, to make sure that all decisions are aligned on this direction. And then we are going to iterate towards this direction with improvement iterations that will range from 1 week to 2 weeks to a month or 3 months as well, as you wish. So once the direction is defined, well, we start by analyzing our current situation. How does our current way of working look like? Which data do we have about our current way of working? And then we start by defining the first target condition, so the first improvement we want to reach. It has a set date and a defined acceptance criteria to say, well, when we reach this acceptance criteria, well, this target condition is successful. Now note that during this planning phase, the team does not know how to reach this target condition. They don't plan on how to reach this target condition. It's only during the execution phase that the team starts to run lots and lots and lots of experiments with different practices. And they run those experiments using the PDCA cycle. So we plan an experiment, an expected outcome. We execute the experiment and collect the data. We analyze the results and compare them with the expected outcome. If successful, we incorporate the change in our baseline. If not, we discard and we start over again. So, in conclusion, because of all the benefits put forward for each and every single practice, adopting continuous integration will predict higher quality and higher throughput. And this has been confirmed by the 2016 peer-reviewed academic paper from Dr. Nicole Forsgren and Jess Humble, the role of continuous delivery in IT and organizational performance, which later fed into the book Accelerate. Who has read the book Accelerate? Well, for the others, it's scientific research, and it confirms everything we knew for the past 20 years, which is important for software delivery and IT delivery in general. And they just confirmed this with scientific research. And it started with this paper, the role of continuous delivery in IT and organizational performance. And so they found out that continuous integration, together with string-based development, are a statistically significant predictor of the adoption of continuous delivery. And adopting continuous delivery predicts higher IT delivery performance. And together with the adoption of lean product management and a generative organizational culture, it will predict higher organizational performance. And there we're speaking money-wise, generating more money, more turnover, more market share. But interestingly, it will also reduce stress, burnout, fatigue, and increase job satisfaction, which in turn will also increase organizational performance. So, if we want to be ahead of our competition, not implementing those 15 practices is actually not an option. Thank you.
You might have mentioned reviews.
No, I haven't mentioned reviews. I've avoided that.
Okay. Do you have any thoughts on reviews?
Yeah, I have thoughts on reviews. But, but that's the reason why I'm stuck on writing this part, because I should do my proper research. So I was a big proponent of reviews because, well, it is said to catch a lot of bugs. Also, it's also the whole premise of open source. If many eyes see the code, it will prevent bugs. Well, by now, and with all the security problems we've seen in open source tools, well, it doesn't stand quite well, this theory. So, my biggest problem is the way code reviews are implemented today, which is mostly using pull requests. The biggest problem with pull requests is that it is a gating process which blocks delivery. And it's only when it's approved that it allows delivery. Well, there's quite a lot of ping pong happening most of the time. Like, yeah, you're waiting for the reviewer, then the reviewer mentions its commands, and then you're waiting for the reviewee because the reviewee started new work because, well, yeah, I'm waiting, so I might start new work. So you also start lots of work in progress at the same time. You have lots of context switching. Now, I've done code reviews with a fairly novice team with string-based development, but we didn't use pull requests. We did like what we call now non-blocking reviews, which was, well, we tracked code reviews in a Kanban board so that we didn't forget that the thing needed review, but it might happen that the code was already in production by the time that it was reviewed. And we had a pretty good set of automated test suites, so that gave us enough confidence that we are not introducing bugs. Also, I'm not expecting code reviews to catch bugs. Whatever everyone pretends that it catches lots of bugs, the inverse is true. And I have to find it back, but I remember coming across a paper that actually did that. They introduced intentional faults in the code and then asked people to review the code to see if they found those faults. And, well, the result was pretty low. But I have to find this paper back. So I'm a bit, yeah, is it valuable? Is it not valuable? So I've done the code reviews with this novice team because I've never got them to do pair programming. They didn't want to do it. So, well, then we will do code reviews. And this was the best we could come with. And it worked pretty well. But yeah, if you want to avoid code reviews, well, mob programming, well, ensemble programming, pair programming, well, this generates flow. We are never blocking. We're pretty sure that what we are producing is good because, well, we have multiple eyes looking at the code, why it is being written, multiple people thinking about the code.
I was just wondering how you felt about warnings. Does that break the agreement to never break the build?
Yeah, so I'm in favor of having warnings that break the build because, well, a warning is a leading indicator of a coming problem in the future. Most of the time, it is a combination of multiple warnings that will give a problem at a certain point.
Yeah, I was thinking specifically with the expanded contract, if you were to introduce the new version of the function, for example, and you use the deprecated attribute, that would introduce warnings, but that could be a good thing to do.
I see where you go. Yeah, that's a fair remark. Well, I would say this is a warning where we would put an exception, but it requires obviously close monitoring of these things. Now, there is a risk that we keep a duplicated method duplicated because, well, we forgot to track this. I'm aware of this. As I've said, it requires more thinking and more work to track this, but with the added benefit that we are introducing flow and reducing time to market. But yeah.
Okay, thank you.
Yeah, so I guess I was wondering if you had any thoughts on how you would like integrate if you had quality metrics. So you had something that not necessarily a test that tested some functionality.
Yeah. Well, my view is that static code analysis is a test. And so, well, it's part of the test suite. Also, static code analysis that check for security problems. Well, the organization with whom I'm working now, well, it's a fintech. We have quite some compliance rules. Well, these things break the build. It's just not an option. Also, common vulnerabilities that are detected in dependencies, it breaks the build.
Hello, yeah, can you hear me? I guess I was thinking things like performance and memory usage.
Yeah.
There's not I guess you want to kind of track them, but it's not necessarily the case that every change would.
So performance test is
never cause.
Yeah. So the performance test is a difficult one because, well, it's more difficult to have a consistent good-bad outcome. Well, it's more balanced. So performance tests usually you need to analyze the results. So you can set a threshold and say, well, if it passes this threshold, it should fail. But then you will have to look at, well, is it actually a failure? Do we need to extend the threshold? Well, it's a slippery slope, because if you start extending, you never know where to end. Now, typically, performance tests are executed later in the execution, so in later stages. So if you have a deployment pipeline that consists of different stages, you start with unit tests, then you start executing different kinds of tests, and one of them is performance tests. Others are security tests. Any other questions? All right. Well, thank you for your time.